We now discuss about integrals that yield inverse trigonometric functions. The formulas are the integral of du all over the square root of a squared minus u squared, which is equal to arc sine of u over a plus c. This can also be written as sine to the negative 1 to indicate the inverse function of sine u all over a plus c. The other one is du all over a squared minus u squared, which is 1 over a arctangent of u over a plus c. Equivalently, 1 over a tangent to the negative 1 u over a plus c. And du all over u, the square root of u squared minus a squared, which is 1 over a arcsecant of u over a plus c, or 1 over a secant to the negative 1 u over a plus c. In all these formulas, a is a constant and u is a function. So among these three formulas, it is the second one that does not involve a radical. For the first and the third, notice that there are radicals involved. For arcsine, it is the square root of a squared minus u squared, and for arcsecant, it is the square root of u squared minus a squared. And take note that the function u also appears outside the radicand for arcsecant. So we take on some examples. Let us evaluate the integral of dx all over the square root of 16 minus 9x squared. So let us examine our radicand. 16 minus 9x squared takes the form a squared minus u squared. So if a squared is 16, that means that a is 4. And if u squared is 9x squared, that means that u is 3x. So we know that du is 3 dx. So we complete the differential 3 dx. So what we'll figure out in our answer is the reciprocal 1/3. And the integral is now of the form du over the square root of a squared minus u squared. And the answer there is arcsine of u, which is 3x all over a, which is 4 plus c. Okay. Second example. Say we have the integral of x dx all over 25 plus x to the 4th. So notice that in our integrand, there is no radical involved. So let us try using the second formula. The denominator takes the form a squared plus u squared. So our a is 5. Since u squared is x to the 4th, that means that u is x squared. We then check our differential, which is 2x dx. So let us rewrite our integrand, x over 25 plus x to the 4th. We know that it lacks 2 to complete our du, so we multiply it by 1/2. Our answer will be 1/2 times The answer to du over a squared plus u squared is 1 over a. Recall that the integral of du all over a squared plus u squared is 1 over a arctangent of u over a plus c. So our a is 5. We'll be getting 1/5 arctangent of u x squared over a, which is 5 plus c. Or that will be 1 over 10 arctangent of x squared all over 5 plus c. We try another one. The integral of, say, dt all over t square root of 9t squared minus 1. So since there is a radical involved and there is a function outside, let us try applying the third formula. The radicand is of the form u squared minus a squared. So a is 1 and u is 3t. Taking the differential of 3t, that will be 3 dt. So we just have to complete our du. 3 dt times 1/3 all over t square root of 9t squared minus 1. And we know that the integral of du over u square root of u squared minus a squared yields the arcsecant function u all over a. So our answer here is 1/3 times 1 over a arcsecant of 3t, that is our u, all over a, or 1/3 arcsecant of 3t plus c. Let us try this one. The integral of d theta all over the square root of e raised to 2 theta minus 4. So, our radicand is e raised to 2 theta minus 4, which takes the form u squared minus a squared. But for radicands of the form u squared minus a squared, it will yield the arcsecant function provided there is a u outside the radicand. So for us to be able to apply the third formula, du all over u square root of u squared minus a squared is 1 over a arcsecant u over a. U squared minus a squared with a u outside. So in this case, in the given problem, our a is 2 and u is e raised to theta. So we need e raised to theta outside the radical for us to yield the arcsecant function. And then we have to check also the du. Taking the differential of u equal to e to the theta, du will be e to the theta d theta. So take note, no? To complete our du, we need e raised to theta. What we only have is d theta. So we need e raised to theta to complete our du, and at the same time, we also need the same function e raised to theta outside radical for us to be able to use the formula. So we'll lock e to the theta. Let me use a different color for that. So e raised to theta d theta all over We need the same term, e to the theta outside the radical, square root of e raised to 2 theta minus 4. Okay? So introducing e to the theta in the numerator and in the denominator will not really change our integrand. No? So we're doing that in order to complete the differential as well as the function u outside the radical. So clearly, we have rewritten our integral into the form du all over u. So let us write that. This is my du over u square root of u squared minus a squared. So we just have to write our final answer, 1 over a, 1/2 arcsecant of e raised to theta all over 2 plus c. Okay? Let us take on another one. Say the integral of dx all over 8 plus 4x plus x squared. So in our integrand, there is no radical involved. So the only formula left for us is the second one that yields the arctangent function. Without the 4x, it will be of the form a squared plus u squared. And that's not really difficult because it will yield 1 over square root of 8, arctangent of x over square root of 8. So the problematic term here is 4x. What do we do with that? We consider these two terms, 4x and x squared. And let us recall the binomial x plus a squared, which is x squared plus 2ax plus a squared. So think of 4x plus x squared or x squared plus 4x as your x squared plus 2ax. We need to add the term a squared so that this trinomial can be written as x plus a. Again, we're going to add a term to 4x plus x squared so that in the end, we'll be able to write that in the form x plus a squared. And the missing term a squared comes from the coefficient of x itself. So for x squared plus 4x, your 2a is 4. Right? The coefficient of x is 2a, and in our problem, it is equal to 4. So this means that a is equal to 4 all over 2 or 2. So the missing term, a squared, the term that we need to add is 4. We write this as dx all over 8 plus, let me write x squared first and then 4x, and I need to add 4. Okay? But of course, we have to counter this by adding negative 4. Otherwise, it will change our problem. No? If we just add 4, then the denominator becomes 12 plus x squared plus 4x, which is totally different from 8 plus 4x plus x squared. Alright? So we need 4 to complete x squared plus 4x as a perfect square trinomial, but we need to subtract 4. Okay. Let me rewrite this as dx all over 8 minus 4 is actually equivalent to 4, and x squared plus 4x plus 4 is now equal to x plus 2 squared. Alright? X squared plus 2ax plus a squared is x plus a. We added 4, so x squared plus 4x plus 4 is equal to x plus 2 squared. Now, take note that our denominator is of the form a squared plus u squared, where a is 2 and u is x plus 2, and the differential du is dx. So this integral is of the form du all over a squared plus u squared. And we know that that is equal to 1 over a, which is 2, arctangent of u, x plus 2 all over a, which is 2 plus c.